Hey everyone, it's question show time. Your questions, my answers, as always, wherever you are on my channel. Question pops into your brain, just write it down. I'll gather them up and I'll answer them here. As you can see, our regular outside green screen is covered in snow, so we're having to use our inside green screen. Kind of miss our Hawaii green screen, but we're back home, so this is what we've got. Stick around. We've got a guest question answerer picked up at the American Astronomical Society, so stay tuned. All right, let's get into the questions. Jim Fogarty. Hi, have any of the current or previous Martian probes included an optical microscope to observe Martian soil to view any bacteria or microscopic life? If not, why not? No, so no rovers, landers that have gone to Mars have had a microscope on board, like a really powerful microscope or an electron microscope or anything like that. And the reason is because it would weigh too much. So when you've got a rover like Curiosity, it only has a set amount of weight dedicated to science payload. And an actual large, really functional microscope would be very, very heavy. Now, Curiosity is equipped with what's called the Mars Hand Lens Imager. And it's just, it's like Curiosity has a magnifying glass that it's carrying, that it can look at rocks and look at things more closely. And so if there were like big fossils, it would be able to see that. Spirit and Opportunity had something similar. They had some level of magnification, but we're probably not going to see like a really powerful microscope going to Mars for a long time. And part of the reason is because it's not that useful. I mean, obviously it would be, if they had no other choice and had to send a great big microscope, there would be value there. But really, consider the little microbe, what people thought were microbes, seen inside that Mars meteorite that was found on Earth. And it turned out that they probably weren't microbes, although they really looked like fossilized little wormies inside a Mars rock. And that's with some of the most powerful microscopes here on Earth. And it still was pretty inconclusive. So it's a lot more useful to go to Mars with things like mass spectrometers and chemical analyzers and things that will provide a lot more science value for the weight that they're going to be able to take and sit down on the surface of Mars. Podkova. Is there a known or theorized phenomenon that could reflect Earth's light back? So, for example, if you had a large enough telescope, you could see dinosaurs in the flesh. Obviously, you'd need a telescope far beyond reality, just a thought exercise. So, I mean, you're using this idea that as we look out into space, we're looking backwards in time. And if we look far enough away, we could look at some object or aliens looking at us from 65 million light years away would see dinosaurs roaming the Earth. And there is something out there that would provide this function for us, and that is a black hole. So black holes, the gravity well on a black hole is so strong that it warps space-time. And when you look at a black hole, you're actually seeing when you see what looks like the event horizon, you're actually seeing light that's being completely curved around the black hole. And some portion of the light that you're seeing is like reflected directly back from the direction that it came. So in theory, right, we could look at a black hole that is 32.5 million light years away, that we could see light that is being reflected from Earth. So Earth's light is the Earth is reflecting light from the sun. The light is going out into space. It is making its way around a black hole, and it's coming back to us, and we would be able to look at it and see how the Earth looked 65 million years ago. But as you said, it's a purely theoretical exercise. We just have no way to resolve objects that small, that far away. Earth-sized worlds orbiting in galaxies 30 plus million light years away, that would be pretty tough. So theoretically, but practically no. Randy Brizendine. I'm still waiting for someone to send a light sail to the sun, unfurl the sail, and see just how fast it could be by the time it passes Earth. It would be an excellent example of acceleration and control to changing direction, etc. during the mission. It would answer questions regarding how to change course while in mid-flight, etc. Nobody's ever going to do that. And the reason is because getting close to the sun is about the most difficult place you can go in the entire solar system. So astronomers can do the math and figure out how many photons at various distances from the sun would have to fall on the light sail to be able to calculate how much acceleration you could get. And when you think about it, right, think about like the orbital mechanics. The Earth is going around the sun at 30 kilometers per second. So if you wanted to get closer to the sun, you'd have to cancel out some of that orbital momentum, some of that orbital velocity that's going with the Earth going around the sun. The Parker Solar Probe is a good example of this. They're having to do many, many flybys of Venus, each time speeding up Venus a little bit in its orbit and therefore slowing down Parker Solar Probe and putting it into an orbit that eventually brings it closer to the sun than any spacecraft that's ever been gotten that close. But it's still going very, very fast. It's still in no way, shape, or form going to be actually falling into the sun. So any solar sail that's launched from the Earth is going to be orbiting the Earth, and it's going to be orbiting the sun in the Earth's velocity. And then it's going to turn the sail in a direction that it starts to get momentum from the sun, from the photons, and it's going to raise its orbit. And so it's going to go in this larger elliptical orbit around the sun. And eventually, the orbit is going to get larger and larger and larger, and eventually maybe it could cross the orbit of Mars and keep going. But it's going to take many, many revolutions around the sun while it's raising its orbit. And if it wants to lower its orbit, it does the opposite thing. It turns its sail in the other direction, and the photons hit it, and it lowers the orbit down. And I guess you could get closer and closer to the sun and eventually, be as close as the Parker Solar Probe. But you'll never be able to have it be stopped orbitally and just have it drop down to the sun and then unfurl the sail and then see how fast it goes away. It's always going to be in orbits. Everything is always in orbits. Vovacat17. Hey Fraser, how will the red dwarfs die? I know the sun isn't massive enough to explode, but it still goes through a rather epic giant stage. I know no red dwarfs will die for the next trillion years, but when they do, what will it look like? So red dwarfs are different from the sun, and the big reason, they have less mass in them, but they're called fully convective. And so when you look at the sun, say the sun has this core where all the fusion is happening, and then surrounding this core is the radiative zone. And the radiative zone is where the photons have to jump from atom to atom, doing this random walk around the inside of the sun, and then eventually they get to the convective zone. And the convective zone is like a big lava lamp, and these blobs of lava are sort of going up to the surface, and they're releasing these photons out into space. And that's why a photon that's generated at the center of the sun could take 100,000 years to be able to actually escape the sun, because it has to do this random walk. So if you've got a red dwarf, the difference between a red dwarf is that they don't have a radiative zone. They are fully convective. And so with our sun dies when it runs out of fuel in the core. It won't be able to use the fuel in the radiative zone, won't be able to use the fuel in the convective zone. It's only the fuel in the core. But with a red dwarf, they're fully convective, so they're constantly mixing. And so they'll eventually use all the fuel in the entire star. And so they'll be turning that hydrogen into helium. And if they're a little bigger, maybe they'll go a little farther than that. And then eventually they will run out of fuel, and they'll just slowly cool down and just become the background temperature of the universe. Shared LTB. Question: is the sensor on a radio telescope similar to the two-dimensional sensor on an optical camera? No. Radio telescopes are very different from what we experience with an optical sensor on a regular telescope, right? When we have a telescope, in fact, your phone camera has a tiny little chip inside of it, and it takes a picture and it puts different colors on all the different pixels on the chip, and then it uses that information to create a photograph. But a radio telescope doesn't work that way. A radio telescope scans the sky at any specific location and measures the strength of the radio, measures the frequency, the wavelength, and then moves a little bit over, and then measures that location, moves a little bit over, and so on and so forth. And so when radio operators are scanning the sky, they're essentially just moving it slowly, bit by bit, and keeping track of what the measurements are at every little location as the radio telescope is moving. Now, there are some versions of radio telescopes that have multiple radio receivers that are built into the telescope. So essentially, it can be tracking multiple different locations that are really close together at the same time as the radio telescope is turning. And so it's kind of like pixels, but not very many, like 10 pixels at a time. But one of the cool things that a radio telescope can do is they can do interferometry. So you can have 2 radio telescopes or 10 radio telescopes, and they're separated far enough away, but they can be imaging some object at the same time, and they act like a telescope that is the size of the distance between those telescopes. And of course, as we saw with the Event Horizon Telescope, if you do it using clocks, even after the fact, you can make a telescope the size of planet Earth. So where radio telescopes don't produce a pixel image in the way that an optical camera does, they make up for it in their ability to act like a telescope the size of planet Earth and resolve features on objects that are incredibly small. So they have their benefits and they have their downsides. Amila Saman. Aliens should be living within at least 100 light years distance to see our technological advancements such as telecommunications, right? Beyond 100 light years, what they would see is Earth 1900s and before. So they won't have many clues of life on Earth unless they get very close, I believe. Yeah, when you look out into space, you're looking backwards in time. And so any aliens looking at us today are going to be seeing how we looked, however long the light took to reach them. So the folks in Alpha Centauri don't know the results of the last presidential election. But if they're 100 light years away, then they're seeing Earth in the 1920s. What they would be able to figure out is sort of a bigger question, right? It all depends on the size of their telescope and the capability for them to be able to sense the atmosphere. What is the difference between, say, the medieval ages, where there's a lot of people that are burning fires for cooking and heating their houses and things like that? Would it be distinguishable from forest fires? What about in the 1800s, when you've got more and more lights concentrated in smaller areas like cities? Would that be detectable? But when you think about just like life itself has been putting out unstable amounts of chemicals into the atmosphere for hundreds of millions of years. So aliens who were more than a couple of hundred light years away would suspect that there was life here on Earth, but they wouldn't necessarily detect right away that there was an advanced civilization that was putting pollution into the air. But then as you get closer and closer to, say, the 1900s, you start to get more of a modern industrial age with coal plants and automobiles and chlorofluorocarbons and things like that, then the evidence would just become overwhelming that there is a civilization here. So it's kind of interesting to think about how, and of course we did an episode about this just a couple of episodes ago, just like what are the signals that we're giving off and how could we use those signals to find other examples of intelligent civilizations out there in the universe at farther and farther distances from us here. It's a fascinating idea. Aeon. Hey Fraser, love your channel. Got a question about the Fermi paradox. Will civilizations actually want to colonize every single star system in the galaxy? I'm surprised so few people question this underlying assumption. It's not necessarily that advanced civilizations would want to settle every single star system in the entire galaxy, but at the very least they would want to scout it out. Right? We haven't settled the Moon, Mars, Saturn, Jupiter, Neptune, Uranus, Pluto, Ceres, other asteroids, but we have scouted them. We have sent a spacecraft there to just look around and figure out what it's all about. And if you're an advanced enough civilization and you're capable of building self-replicating robot probes where you send one probe to a star system and then it builds 1,000 copies, sends off to other places, they build 1,000 copies, goes off to other places, and within a couple of million years you start to get reports back of every corner of the entire galaxy that you live in, that's useful information. So that, it will map out all of the places in the entire galaxy that have civilizations, which are the places that are interesting, scientifically interesting, what are some of the extremes, what are some of the places that you might want to avoid. all of that information is very useful. And as we start to progress in our technology, we'll probably, and it becomes feasible for us to be able to do this, I can't see any reason why we wouldn't want to at least know what's in the galaxy from side to side, from top to bottom, and try to build a catalog of everything that's out there, at least for our knowledge. And then maybe later on, we'll actually want to pick and choose the absolute best places that we're going to want to go. So I think the best reason to think why there could be at least self-replicating robot probes across the entire galaxy is just purely for knowledge. Marco Cambrai. My curiosity question is, in between interstellar dust, what is expanding? Is it the space in between the molecules, or what, the space between planets? Any further explanation? So at the largest scales, the distance between galaxy clusters is growing. When we look in all directions, we see galaxies speeding away from us, whether we look to the left, to the right, to the top, to the bottom. And if you could move to any one of those galaxies and look at the Milky Way, it would look like the Milky Way is moving away from us. So wherever you go in the universe, everything looks like it's all getting away from you. And the way you would understand that is that the universe is expanding. But really, the best way to sort of think of it is that, in fact, the universe is getting less dense everywhere you go. And of course, there's these analogies, right? The raisin bread analogy, where you let raisin bread rise and the raisins have more space. Wherever raisin you're on, you're seeing other raisins move away from you. I always imagine this idea of just like a grid of like graph paper, but it's 3 dimensions, it goes on forever, and the grid is just getting bigger, right? That is at the largest scales, at the galaxy level scale. But at the smallest scales, other forces are stronger. So at the scale of even the Milky Way galaxy, the gravity that holds the Milky Way together from the halo of dark matter that surrounds us is stronger than that expansion that's going on across the universe. And so the galaxy isn't spreading apart. Same thing with the solar system. The sun holding the planets with the gravity is stronger than this expansion of space. Same thing with the molecules in your body, molecules and gas. So at the smaller levels, other forces are stronger, and so that's why not everything is kind of spreading apart. But once you get to those biggest scales in the universe, then it's that expansion that is taking over and making everything move farther and farther away from each other. Seth Cooper. So this is a little off topic, but I had a thought experiment and I kind of hit a limitation with knowledge. I was hoping you or the community could help. So the conversation today is that we need to become more in balance with nature, but our species society seems to have found itself outpacing nature. So should we become more in balance with nature, or should we continue marching forward and learn how to artificially create natural processes so that we have more control over the natural world? I was just trying to think that if we pass the point of no return for the climate, we could push through to just being in control of our environment. Thank you for all the great content. Wherever we go as human beings, we try to kind of dominate and take control of our local environment. You see that in, you don't live in the middle of the forest, you live in a house because a house is dry, and you can regulate the temperature, and you can regulate the amount of moisture that's falling on your head, and where the food is located, and all that kind of stuff. And a city is a bigger version of that, where we've organized the level of the transportation and where you get your food from, and so on and so forth. And that is just like a city is related to the individuals that live in the city and how much control they want to have over their local environment. And we are absolutely changing the environment of planet Earth through the exhaust gases from our carbon dioxide, through methane and things like that. And so we are pushing the Earth into places that it hasn't been for a very, very long time. And it's clear that we have no control over this process. We could have control, but right now the sort of short-term desire for better standard of living, for being able to fly around the planet, being able to drive our cars, being able to go to Costco and buy things in bulk, right? This is the way we go. And I think at this point, as scary as this sounds, it is within our ability to more or less have control over all of planet Earth. And this is this idea of a type 1 civilization, that we have become masters of the entire planet. and could shepherd it, steward it towards some idealized version of itself. But like, by what judgment do you decide what is an idealized version? Many people would think that the idealized version is no human beings on it whatsoever, and just let nature run its course forever until the sun dies. But another possible, like Earth could be more biodiverse, which is sort of an interesting idea. There are places that are incredibly biodiverse. Like in Costa Rica, there's like this one little part of Costa Rica that has more species of trees on it than the rest of North America combined. That's really interesting. Could we encourage more diversity? So I don't think that we as human beings are wise enough yet to know what's best for planet Earth. We're definitely taking actions that are going to impact planet Earth, and I think we can pretty safely say that they're not very wise. And I think it's an interesting idea that maybe at some point we could gain a level of wisdom, that we could live on a planet that is like the best possible version of itself, whatever that means, right? By whatever measurement you would decide. And I think we're pretty close to having the kind of technology to be able to do that. But right now we are running sort of headlong in an experiment that we don't know what the outcome is, and it's probably bad. So I think it's an interesting idea, and I can imagine it being kind of inevitable that in the future, I hope we will get to this point where we will be able to take better care of the Earth, and maybe even better care of the Earth than the universe has taken care of it, because the universe, as we know, wants to kill us. So it's an interesting idea, and but I hope that we approach it very carefully and very slowly with a lot of wisdom, because right now, I don't think we're there. Sazzy Plu. Do black holes come in a multitude of shapes with a variety of dimensions like that of galaxies, or is there just the one commonly drawn black hole that's more or less hole-like? Well, there's this famous quote that black holes are neither black nor holes, right? They're not black because they're actually essentially absorbing all of the radiation that's falling into them, and they don't emit any light whatsoever, so they're kind of invisible. And they're not holes. That graphic that you see of a black hole that sort of looks like this funnel that's going down is sort of it's trying to give a representation of how space-time is warped, but it's really only doing it in 2 dimensions. The best idea of what a black hole is, when you sort of think about it, just take the Earth, right? And think about the gravity on the Earth. Everything on the Earth is sort of pulling towards the center of the Earth. Now, imagine if the Earth had way more gravity, and everything would be pulling towards the center of the Earth. And imagine if Earth had so much gravity that light couldn't escape. It was that strong. And now you couldn't see it because the light wasn't there, but still you'd have all this, right? All of this incredible, intense gravity pulling into this one central spot, the singularity. So the thing that does change how a black hole might appear depends on its spin. So a black hole that isn't spinning is going to be essentially a sphere, a perfect sphere. But as the black hole spins faster and faster and faster, the event horizon, sort of that point where light can and can't escape from the black hole, that flattens out. And so as a black hole reaches literally the limits that are predicted by Einstein, as it starts to approach, I forget what the number is, like some significant portion of the speed of light, the event horizon has flattened out. But it can never flatten out at the point where the singularity will actually be revealed. And that is sort of the limits of it. And so black holes, if you could get really close and see how they might look, they would look different levels of flattened, rotating spheres, oblate spheroids, depending on the speed that they're rotating. But apart from that, there's no real way to distinguish them apart from the mass of the black hole, and that defines the size of the event horizon. Halil Zelenka. If you have a high-tech spacefaring civilization building megastructures in multiple star systems, by what mechanism would it go extinct? So this is back to the conversation that I was having with Adam Frank, and this idea that civilizations may last some period of time and then they go extinct. And so we may not see any evidence of alien civilizations here on Earth, and then maybe later on someone will come back and resettle Earth, and aliens are moving back and forth throughout the entire Milky Way. And so then, like, what would cause a civilization to go extinct? We don't know. We've seen examples of civilizations going extinct in the past. There's lots and lots of examples of those. And usually it's because the weather patterns change and droughts cause food production to go down and the civilization collapses, or you get wars with one civilization overcoming another one. And there's been plenty of science fiction that's thought about this idea of like precursor civilizations. They did a great job of this in Mass Effect, and I've read a bunch of other sci-fi books. I'm sure people in the comments will recommend some as well, where they imagine some incredibly powerful, the Expanse series, you imagine some incredibly powerful ancient civilization at the height of its technology, and then for some mysterious reason, it was wiped out, maybe leaving artifacts behind that showed its level of technology. There could be the reasons that I described: war, lack of resources, and there could be things that we can't possibly predict, that they are science fiction reasons why bad things happen to large civilizations. And the only way we'll be able to find that out is when we run across them, right? Like the ancient Romans couldn't have imagined nuclear annihilation. And yet here we are today with thousands of nuclear weapons around planet Earth, and we can imagine it. The ancient Romans probably couldn't have imagined an asteroid strike or a worldwide pandemic or an AI apocalypse or gray goo, right? Like there's a ton of things, or some physics experiment that turns the entire universe into vacuum energy. So who knows what reason civilizations might go extinct in the future? That's the idea of the Great Filter. In STEAM, are there any models predicting how luminosity changes in the final stages of a star before going supernova? Is there any place I can go and see a graph for Betelgeuse's recent luminosity changes? Great timing. When we were at the American Astronomical Society meeting, I ran into Stella Kafka, who has been a guest on the Weekly Space Hangout in the past. She works at the American Association of Variable Star Observers and has been watching Betelgeuse very carefully. They have been for decades. And she actually had a graph of Betelgeuse's luminosity changes on her computer. And so I passed your question along to her. She answered it. So hopefully this helps. One interesting side note, since I did that video on Betelgeuse, it is actually decreased in brightness. So it's continuing to dim. So it's now down to about magnitude 1.5, which is kind of amazing. So still don't know why. Don't think it's going to explode, but still.
So the answer is yes. There are multiple models that are showcasing how a star like Betelgeuse will end up as a supernova. There are two main ideas. One, that the eruption will be bimodal, as in material is going to explode from the two poles of the star. And another one that in general is going to be spherically symmetric, as in the star is going to explode as a whole. Now, these are models, right? And variable stars are variable for a reason. They don't necessarily follow models. So until we see Betelgeuse going off, we don't really know how it will end up. At the same time, we have been observing Betelgeuse in principle for thousands of years as humans. But when it comes to recorded brightness or luminosity variations, we do have at least 100 years of data from the AAVSO database. And actually, one of the things I would like to show you is a long-term light curve of the star. So this is brightness variation, luminosity variation with time. And what you see here is a little messy plot of all the data points that have been collected for more than 100 years by non-professional, by amateur astronomers looking through, actually with their naked eyes. Betelgeuse is bright enough to be able to actually see it with your eyes and comparing its brightness with other stars in its vicinity. What you see here are digital data. So from one point on, what digital means became available to amateur astronomers. We have individuals who purchase cameras or purchase means in order to follow these stars' luminosity changes with digital means. So what you see here is a V luminosity variation over the last couple of years, and this is the B as in blue, how the star is behaving in blue. So you can see pretty much the color of the star, B minus V, more or less being the same, which is actually one way that will help us interpret the data once a phenomenon, which is actually presented here, will evolve and be completed, hopefully over the next year or so. So Betelgeuse is one of those stars that have been observed very frequently. It's really bright. And actually this is one of the challenges of observing Betelgeuse. It's really bright. So big telescopes cannot observe its flux variations. You do need small telescopes and you do need dedicated observers like the observers of the AAVSO to actually take those flux measurements for professional astronomers to come back and understand the behavior of such an interesting system.
Okay, thanks, Stella. That was awesome. I hope you enjoyed that. We've got many more of these guest questions from the AAS coming up, so stay tuned. All right, well, once again, this ends another question show. As always, thank you everyone for sending in your questions. Question pops into your brain, write it down, I'll gather them up, and I'll answer them here, and I'll see you next week.